exploration of Sierpinski's triangle made by Amy Gurecki and Tiffany Jenkins.
The perimeter of Sierpinski's triangle. Today we will be exploring Sierpinski's triangle. We will first begin by finding a basic formula for a perimeter. We will be starting with an equilateral triangle with sides of 1 unit length in our example. Piece of 1 will equal to 3 because the perimeter is the addition of the 3 sides of our equilateral triangle. By constructing the midpoints of our original triangle and constructing a segment to each point, we will see another triangle is formed within. The sides of the inner triangle are length of 1/2, therefore piece of 2 is equal to 3 plus 3/2. We have now begun our process in iterating our Sierpinski triangle. Each time that we iterate, we increase the number of our triangles by a factor of 3. Each will have a perimeter of 1/2 the previous triangle's perimeter. Therefore, piece of 3 is equal to piece of 2 plus 9/4. Piece of 4 is equal to piece of 3 plus 27/8. And piece of 5 is equal to piece of 4 plus 81/16. We begin to see a pattern and can now derive a basic formula for the perimeter. Let us call this piece of n. By looking at the pattern, we can derive piece of n to equal the summation from n equals 1 to infinity. 3 times 3/2 to the n minus 1 power. By taking the limit of piece of n as n goes to infinity, we see that the perimeter gets larger and larger. Therefore, the perimeter of the Sierpinski's triangle is infinite.
The area of Sierpinski's triangle. We will now try to find a basic formula for the area. Because we have chosen to use an equilateral triangle in our illustration, we know the area of our first triangle, a sub 1, will equal the square root of 3/4. We know this because our original equilateral triangle has sides of 1 unit length. We find a sub 2 to equal a sub 1 minus 1/4 times the square root of 3/4 because when we constructed the midpoints and the segments from each midpoint, we now had 4 triangles. In order to find this new area for a sub 2, we have to take the inner triangle constructed by the midpoints, as seen in blue, and subtract it from the area of the original triangle. We do this because we no longer want to account for this area and are only concerned in finding the area of the 3 remaining triangles. Therefore, we must subtract 1/4 times the area of the original triangle. A sub 3 will equal a sub 2 minus 3/16 times the square root of 3/4 by the same reasoning. A sub 4 is equal to a sub 3 minus 9/64 times the square root of 3/4. We begin to see a pattern and can now derive a basic formula for the area. Let us call this a sub n. By looking at the pattern, we can derive a sub n to equal the square root of 3/4 minus the summation from I equals 1 to infinity, 1/4 to the I, times the square root of 3/4 times 3 to the I minus 1. To cancel out the minus 1, we will multiply 3/3 and simplify. We would like I to equal 0 in our summation, so that we can see a sub 1, our original area. To do this, we will subtract 1 from the summation as shown. We notice that 3/4 to the I is a geometric series. We can use this fact and substitute 3/4 into the equation 1/1 minus r. By doing this, we get the equation shown. By simplifying, we find the area will equal 0. By taking the limit of a sub n as n goes to infinity, we see that the area gets smaller and smaller. This is because 3/4 is less than 1. Therefore, the area of Sierpinski's triangle goes to 0 as n goes to infinity. Ta-da!